All right. Hello, welcome back. So we have covered so far only kinematics of rigid bodies, and specifically we have been looking at orientation and rotation and angular velocities. As you can see, when we go from translation to orientation, things become a little complicated. But now we are equipped with enough ways to think about orientation and rotation in 3D, and we are ready to tackle the next question, dynamics. So similar to particle dynamics is describing the relationship between forces or moments and movement. So now what we are going to do is try to build these relationships between moments, which are kind of rotational version of forces, and rotation and angular accelerations of the body. So that's what we are going to do in the next few videos. Before doing that, we need one more concept that we can use to make this relationship, and that is the extension of inertia into 3D rotational domains. So just to refresh your memories, so as a let's just start from here. So as a reminder, look way back early in this course. So remember, we had a single particle happily going about its business. I had a point P, and the position, we called it rho. So the angular momentum, which was a vector about point P, was rho. This had some mass m, rho cross m rho dot. And this was true for any point P. So rho is the relative position of mass with respect to P, and rho dot is the change of that vector, the absolute change. What you can do to kind of try to simplify your calculations, let me try another color. No, not this color. This one. Go. What I can do to write this rho dot in the inertia frame, let me attach a reference frame. So I'm going to point it toward the object. So this is a three-dimensional reference frame that as the particle is moving around, it kind of tracks it. And so it is also rotating with some angular velocity omega. And for now, let's pretend P is fixed, but that doesn't matter. No, let's keep P as moving. Who cares? Doesn't matter really here. So this frame is rotating as the particle moves. So in this relative, in this local frame that is moving, the red one, what I can do is write this as rho cross m and rho dot. We can write it as rho dot relative in this frame plus omega cross rho to include the effects of the frame rotating itself. And now I'm going to make another assumption. Just assume rho dot relative is 0. So in other words, m is fixed in in this little, let's call it XYZ. XYZ in XYZ frame. So this is just a reminder. So in this case, I'm going to write it down. Under this assumption, h of p is that term is 0, so rho cross m times omega cross rho. That's the angular velocity if we pretend m is fixed in this frame. All right, so that's enough for the reminder. Now let's go to our rigid body case. Now consider I have again my inertial frame, a rigid body, some point P, and I'm going to do the same thing. Have this frame fixed to the body and it rotates with the body. Now let's look at a particle inside the body. Let's call it, for the sake of argument, let's call it dm instead of m. Just a tiny infinitesimal particle within the rigid body. So nothing has changed for that particular body, for that particular particle. Still, I can use this equation to find the angular momentum of that particle about this reference point. And I can do the same for any arbitrary particle in the body. And what it turns out, let me do some heading. Now consider a rigid body. Let me finish this, and a fixed frame that moves with the body. Okay, sorry, I should have written it before. So blah 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 blah, I can calculate the angular momentum of any particle dm about that point. And what I can do is sum all of these angular momenta about that point to find the total angular momentum of the entire body, the same way we were doing it for a system of particles where particles were kind of separate. We can do the same. So angular momentum of the whole body in this case is the sum of all these little DHPs, and by DHP I mean kind of using this equation, and that is, well, let me change that. Because we are working in a continuum, essentially that summation becomes an integral of these rho cross m times omega cross rho. And in this case, instead of having m, I have these little tiny particle in the body, and the integral is over all the m's. So maybe let me rearrange it so it looks a little nicer. Integral of over m rho cross omega cross rho dm. This is cross rho. So if all of these vectors are kind of absolute vectors, but I can write them in any frame that I want. So I decide to write them and kind of find the components of each of these in the little XYZ. Again, I forgot the name. So XYZ, and this is rho. I can write the components of these vectors along the little XYZ, my moving body fixed frame. So in this case, the angular momentum becomes integral over m of xi, that looks like a j, xi plus yj plus zk, that is my rho, cross my omega is omega xi plus omega yj plus omega zk, cross again rho xi plus yj plus zk. Finally, dm. If you do all the cross products, some of them will I cross I, for instance, is 0 and so on. If you keep doing that, what you end up with is kind of a lengthy equation. So I'm going to break it down. So this angular momentum, oops, don't know, where did it go? What happened? So I have, why is it doing that? Don't do this. Ixx, a shorthand form. I'll define it later. Ixx omega x plus I xy omega y plus some ix z omega z along I plus iyy. No, let me write it. Omega yx omega x plus iyy omega y plus iyz omega z along j plus I zx omega x plus I zy omega y I z omega z. Okay. And then what are these I somethings? Ixx is something we had seen before. So no, y squared plus z squared dm and summation over m. So this is the same moment of inertia that we had seen before. Distance from the x-axis squared times the tiny mass and integrated over the entire mass of the object. Similarly, Iyy is integral of x squared plus z squared dm summation over m, and Izz is integral over m of x squared plus y squared dm. So these things, let me do another color, are called, as we had before, moments of inertia, and each one is about one of these axes. Moment of inertia about x, moment of inertia about y, and moment of inertia about z. The other terms are these I, xy, xz, and so on. So as it turns out, Ixy is the same as Iyx, and that is the integral of xy dm. Oh, actually, minus negative of that. Don't forget about the negative. Ixz equals Izx equals integral over m of xz dm, and which one do I need? X, yz. Yz equals Izzy equals integral of y, z, dm, or all of them negative. I keep forgetting. This is minus equals minus integral of this. And these ones, which are equally important as the moment of inertia, are called, oops, I can't spell, products of inertia. So when you have these integrals calculated, you can go and use this equation on top to calculate, for instance, the angular momentum of a particle, angular momentum of a body. It is convenient to look at, why does the source change so much? To write the same equation in matrix form. And I can write HP. I'm going to use this notation to mention that this is a matrix, a column matrix representing that vector. This one equals a big matrix I times the vector omega, and this I is, as you can imagine, IXX, IXY, IXZ. I need a little bigger. IYX, IYY, IYZ, IZX, IZY, IZZ. So if you define this matrix, you can very easily go from your angular velocity to your angular momentum. And this is a very important matrix. It's called inertia matrix or inertia tensor. And before, when we were talking about moment of inertia, it was usually in a 2D plane. We were looking at planar dynamics. So we always had moment of inertia about a point. If we were too generous, it was about an axis. But in general, in 3D movement, the inertia matrix is defined for a certain frame. So for a certain x, y, and z. So you cannot just say my inertia, momentum inertia in 3D is, I don't know, this value. You need all of these moments of inertia and products of inertia to fully describe how the inertia of the body is behaving in a rotational sense. So a little dry, I would say, but the end result is quite convenient. And you can see we can use, for instance, a nice form of equation: velocities multiplied by some inertials equals momentum. And this I shows up in many other places, and it's a good form. So one thing I should also mention, the textbook uses tensor notation. Tensor is essentially an extended 2D version of a vector. So you can do dot product and cross products of tensors and vectors. It's a slightly different notation than matrix notation. I'm going to continue using matrix notation, mostly because that's what I'm more comfortable with. And they are quite easy, especially, I don't know, in MATLAB. You can just type in your variables into a matrix form, although tensor is not significantly more difficult. But I'm going to stick with matrix notation. You will see a slightly different shape of formulas in the textbook, but know that they are the same, just with two different notations. All right, so that is about inertia matrix and inertia in a rotational domain. Is it called inertia matrix? I don't know. I don't know. Maybe it's called something else. But anyways, let's call them inertial matrix for now. All right, in the next video, we will look into more stuff about dynamics. So, all right, until then.